Yes, so today we discuss cosmic strings. So remember last time we were discussing domain walls and there was some notion of topology. So this is a generalization of that concept. But let me start with the reviews once again. There are some excellent books and papers to read. So I mentioned solitons and particles last time. There's an excellent review on vortices and monopoles by John Preskill. This you can find online. There's a review by Hindmarsh and Kibble. And then there's the book by Vilenkin and Shellard. So these are excellent references to get started. Let's start with discussing the topology that's involved in the existence of cosmic strings. So basically, what you have is some sort of order parameter, this field phi, which is of course a function of space. Maybe you can think of it as a function of space, right? So the assumption is that you assume that phi is in the vacuum manifold at all times. So the vacuum manifold is defined to be the least energy configuration, assuming that phi takes on some constant value throughout space. Okay. So that's the vacuum manifold over here, and this is the boundary of your spatial domain. So, for example, if you're in one dimension, then it's the endpoints, x equal to minus infinity and plus infinity. If you're in a plane, then it could be the circle at infinity, spatial infinity. And if you're in 3 dimensions, then it's a sphere at spatial infinity. So at spatial infinity, phi defines a mapping from your boundary of that spatial domain to the vacuum manifold. Okay, so it's a map. For every point on the spatial domain, you have a point on the vacuum manifold. So topological defects exist if, when the spatial boundary, you bring in the spatial boundary as contracted to a point, its image on the vacuum manifold cannot be contracted to a point. So that would happen if there's some sort of hole in the hole in quotations, because a hole can be 2-dimensional, 3-dimensional, or so on. If there's a hole over here, and if this mapping sort of wraps around the hole, then you shrink the spatial surface, but this cannot shrink beyond the hole. So then you get some obstruction to shrinking, and that defines the topology. So that defines there's a topological defect in your system. So this has been a study in topology, and mathematicians characterize the topology by homotopy groups, and they're denoted by pi n of m, where little n is the dimension of the sphere over here, and m is the manifold that you're considering. So it's quite general. Now, in particle physics, you have symmetry breaking. So some group G breaks down to some group H. And we discussed some of this last time when we said SU5 breaks to SU3 cross SU2 cross U1, right? Then it turns out, and this requires a little more thought, is that the vacuum manifold is the coset space G divided by H. So G over H is the vacuum manifold. And so what you're interested in particle physics is pi n of G over H. And if pi n of G over H is non-trivial, then that means that there are mappings which cannot be shrunk to a point, and so there are some topological defects. So the exercise becomes if a particle physicist tells you what is G and what is H, then the mathematician has already calculated pi n of G over H, and you can look it up in tables, and you can see whether it's trivial or non-trivial, and that tells you that there's a defect or not. The case of cosmic strings is in 2 dimensions. So the boundary is just a circle. And so, so this little n is 1, and you're interested in pi1 of G over H. And mathematicians have calculated homotopy groups for lots of manifolds. So the simple example in 2 dimensions is that this is the boundary of a spatial domain. It's a circle at infinity, and it's characterized by some angle theta. And then you have a mapping to, say, the vacuum manifold might be a circle as well. And this is an example I will describe in more detail. Then a non-trivial mapping is that, say, alpha, this angle alpha on this side is just equal to theta. So as you shrink this blue circle down to a point, you have to continue to go around this. There's no way to shrink this mapping, because as you go around here, you're going around over here as well. So this would be an example of a non-trivial mapping. All right, so let's consider a sort of the prototype string. This is the abelian Higgs model. It has a complex scalar field, this phi, and it has a gauge field, which I call a mu. This covariant derivative is d mu plus I e a mu. That's the gradient squared term, the gradient energy term for the scalar field. Then you have the usual Maxwell gauge field term, and then this is the potential. And you can see that the potential is phi squared minus eta squared whole squared. So the minimum value of this is 0. And 0 means that mod phi is equal to eta. But remember that mod phi is a complex scalar field. So the vacuum manifold is actually a circle, because phi can be mod some value, eta actually, e to the I times the angle, right? So the vacuum manifold is a circle, and once again you can wrap around the circle as you go around the spatial circle, and that means that there are topological defects in here in 2 dimensions. Yeah. And then you can solve the equations of motion explicitly, and what you find is that there's a cylindrically symmetric solution in which the magnetic field is maximum at r equal to 0, and then falls off, r being the cylindrical radial coordinate. And this mod phi is 0 at r equal to 0, and then goes to its asymptotic value. And so this is in 2 dimensions. So what you've shown is that in 2 dimensions there is some let's think of 2 dimensions. So you have a magnetic field in some region, in a tube-like region. Sorry, so in 2 dimensions it would just be a point-like region. But then you can lift the whole plane, and the location of this phi equal to 0, for example, would lift along a curve, and that would become a string. And there is some thickness to this. So the thickness is given by the inverse mass of phi and of the different kinds of particles. And inside this tube is a magnetic field. So basically the string is a little tube, a very thin tube, but it can be arbitrarily long, of magnetic field. Okay? And the energy per unit length of this tube is given by eta squared, eta being the expectation value. And if you take eta, the scale, to be the grand unified scale, then Newton's constant times mu. Remember, Newton's constant is 1 over Planck mass squared. So this is a dimensionless quantity, and it can be 10 to the minus 6 to 10 to the minus 10. Okay? All right. So now let's come to cosmology. So we've discussed the mathematics, the topological classification. We've discussed the sort of formal solution of this topological defect, but how does it come about in cosmology? And this again goes back to what I was saying last time, is that the symmetry breaking implies that there's formation of domains. Okay? So any point on this vacuum manifold is as good as any other point. Okay? So if you have to go into the vacuum, then you can choose to go in one place or the other. It's completely symmetric. And so, so you have some sort of domain formation where these arrows represent different values of phi. Okay? And once you have this, then just by chance you will be wrapping around this vacuum manifold in some region, and you will be forced to have a string in that region. Now, this is also the basis for topological defect formation in cosmology. I mean, of course, in cosmology, we've been doing this for a while, but condensed matter people have been doing this even longer. And some of this discussion has been tested in helium-3, for example. In superconductors, you must have seen Abrikosov a lattice of vortices. And so those are all basically cosmic strings, but in condensed matter systems. So the point is that if strings exist in the theory, then they are bound to exist in cosmology. Just by the random nature of this, that you're throwing phases at random in different domains, you can find the probability of forming a string, and it's relatively large. It's order 1 that you'll form a string. So, if this whole setup, like this distribution of domains, happens, I mean, it's bound to. So the strings are bound to exist in cosmology, unless special arrangements are made to eliminate them. I mean, unless you say, oh well, strings formed, but then there was inflation, and you got rid of the. That's a different story. Okay, so then you ask, well, when they are formed, what do the strings look like? And so this was studied by doing simulations. What you do is, let's say you have a lattice. And you know that you have to be on a vacuum manifold, right? So there's some given by some angle theta, that's a circle. So you just randomly select 0 is somewhere, pi by 2, maybe pi by 4, minus pi by 3, whatever. You distribute phases randomly, so you're randomly at different points and on different lattice sites. And then you check for the winding. Am I going around the whole vacuum manifold when I go around a circle over here? If I wind around the circle, if those angles wind around a circle, then I must have a string coming through this point. Okay. So you can do this on a computer, and then what you find is that you get strings which are closed. So you get closed strings. So those are called loops. So then you ask, well, what's the size distribution of these loops? And what you find is that the number density of loops of a size r is dr by r to the 4. Okay? And this is a scale invariant spectrum of these loops. It's scale invariant because there's no other scale in the problem except for the size of the loop. You see, if you work out the dimensions, this is length divided by length to the 4, so it's 1 over length cube, and the number density is 1 over some number divided by length cube. So this is the size distribution of loops. You can see that there are many more loops at small size than there are of big size, right? Because it's falling off as r to the 4. And then if you take an individual string and you ask what is its shape, how zigzag is the string, then you find that the length, so if you have some string which is doing this, then you ask, well, how does the length of the string, L, depend on the distance r? Okay? And what you find is that L goes as r squared, so it's actually a Brownian walk. Okay? So that's the quadratic relation is a signature of a Brownian walk. Well, the most surprising thing is that about 80% of the strings are in infinite strings, in strings that don't actually close on themselves. They just keep going on forever. And this is an important fact for cosmology, because if there were only loops, then the loops would shrink and collapse and would go away. But if you have these long infinite strings, then the strings can never go away. Yeah, even on evolution, you're stuck with this infinite random walk. And you might recall similar results for domain walls, in which there was one big domain wall, basically an infinite domain wall with complicated topology. So, okay, so a box of strings might look like this. It's hard to tell, but there might be some loops over here, and then there are infinite strings. So then you ask, once I form these strings, how do they evolve? So, so here again, you know the fundamental theory, you know the abelian Higgs model. So in principle, you can just evolve the field equations and see what happens. But that's kind of expensive. So what you realize is that the length of strings is given by some cosmological scale, which might be 10 to the 27 centimeters. But the thickness of the string is given by the inverse mass of particles, which might be something like 10 to the minus 24 centimeters. Okay? So this ratio is what? Something like 10 to the 50 or something. And so the thickness of the string is completely negligible compared to the sizes of these strings. Yeah? So a good approximation would be that you ignore the thickness of the string. And so you start with a field theory action, and then again, you can do various operations and reduce it to what is the Nambu-Goto approximation, which is that it is just minus the energy per unit length of the string times the area of the world sheet. So as the string is moving, it is sweeping out a certain area, and so the action is proportional to that area. So this is what's the Nambu-Goto approximation, or the zero thickness approximation. And it's a reasonable approximation, except when strings cross, because then the thickness becomes important, right? Or in places where the string becomes very curved, the radius of curvature becomes comparable to the thickness. And both of these things actually happen for cosmic strings. So when strings cross, for example, here there's a string going around and then coming back, and these paths are crossing, then they actually break up, and you get a loop and the other part of the string. And I've drawn it with slight corners over here, and it is true that after crossing and reconnecting, there will be corners, and these corners are called kinks on the string. Okay? And it turns out that the probability of reconnection, so the probability, I mean, you can send strings at 90 degrees, you can send them at various angles, or you can send them at different velocities, and in all cases, it turns out that they reconnect. Actually, almost in all cases, unless you send at velocities of 0.999 or something, they may not reconnect. In string theory, there are cosmic string solutions, and there the situation is a bit different. because you have extra dimensions, and then strings might miss each other in the extra dimensions, and then the probability is not 1, but something else. Okay? So the usual way of studying string evolution after that formation stage is to use this Nambu-Goto dynamics, so the strings are moving around, minimizing the worldsheet area, except when there's an intersection. And when there's an intersection, you by hand kind of reconnect them, and then you again let evolve the network further. So lots of people have done these kind of simulations, and after a while, the string network looks like this. Okay? So here you can see lots of little loops. All of these little dots that you see are tiny loops of string. And then there are some long strings which are running across the box. Okay, this is a periodic box. A string might go out of the box, but it might come back in. Okay, so you see that the string network looks quite fragmented. It has lots of loops and lots of these random infinite strings. So we are going to discuss gravitational wave emission. So we have to consider this dynamics a little more in detail. So let's look at the dynamics of a loop of cosmic string. So let's assume that the loop is in Minkowski background, not in Friedman-Robertson-Walker background, but in Minkowski background. And you can choose the coordinates on the string itself and on the string worldsheet. And so there's a particular choice of worldsheet parameterization. And then you can solve the equations of motion. It just turns out to be like a wave equation in one dimension. So x is the position of the string at time t at position sigma along the string. And that just turns out to be a vector function, this a of t minus sigma, and a vector function b of t plus sigma. So these are the so-called left and right movers on the string. But there's a constraint. The constraint is that a prime, the derivative of a, the magnitude of the derivative of this vector a is 1, and the magnitude of the derivative of vector of b is also 1. So a convenient way to picture what's happening is you draw a sphere. This is a sphere, and I'm going to draw a prime and b prime on the sphere, because the modulus of a prime is 1 and the modulus of b prime is 1, so they all lie on the sphere. And a prime is some trajectory, some function that goes around this sphere, and b prime is some other trajectory. But if you draw two trajectories on a sphere, it's very likely that they will intersect. So there might be intersection points like this, and these are special points. These are singularities. Because the intersection of a prime and b prime implies that the derivative of x with respect to time, so the velocity is just half a prime plus b prime. You can figure that out from here, a prime plus b prime. But then if b prime is equal to a prime, then this is just a prime. And so at this intersection point, if you take the magnitude of this velocity, then that is 1. But I'm working in units where the speed of light is 1. So this means that there's a point on the loop where the string moves at the speed of light. And that point is called a cusp. And as you can imagine, if there's a charged particle or something that moves at the speed of light, it emits a lot of radiation. And so that's what's going to happen over here. So the cusp looks like a little sharp point over here, which just occurs for one instant. It's like a whip. You whip something, and the tip of the whip goes at a very high speed for just one instant, and so that's the cusp. And field theory simulations of a cusp, and you can see that the Nambu-Goto. So far I was discussing the Nambu-Goto evolution, right? So the cusp is a Nambu-Goto phenomenon. You might say, well, the Nambu-Goto was an approximation to the field theory, And you know that the Nambu-Goto breaks down when at high regions of high curvature, such as at a cusp. So what happens if you do a field theory simulation of a cusp? And what they find is that the Nambu-Goto would give you something like this, but the field theory actually smooths it out a little bit, and then a little part of the string flies off. Because the cusp is sort of a string going up and a string coming down, and so there's some annihilation of the string at the tip. I already mentioned intercommuting. Intercommuting, that are those reconnections, they imply discontinuities in the A prime and B prime curves. So remember, I drew some sharp corners. So if you have these sharp corners over here, they actually imply that these curves that I drew, nice and smooth over here, I drew some nice and smooth curves over here, they need not be smooth, they can be broken. So they, for example, A prime is broken over here. In this case, there's a sudden jump of the tangent vector to the string. A prime is related to the tangent vector. So, so you have a sudden jump in the tangent vector to the string, which means that you have a sharp corner. And so you will, in general, when you have a string reconnection, there are two kinks. One is left moving and one is right moving. So there are sharp pieces on the string which are moving along the string. All right. So the other question you might ask is, well, now a loop can be any shape. What's the typical shape of a loop? So what we did in this study was that we took some very complicated loop and we let it evolve, and it fragmented, and then we said, is there something we can say about the final loop that does not fragment any further? And so I think you'll enjoy this movie. Here, there's a complicated loop, and it evolves, and you will see lots of fragmentation. So after seeing this movie, maybe you can kind of guess what a typical loop looks like. The typical loop is something like this, or like this, right? These are typical loops. You can see they're very planar. They have maybe 4 or 5 corners to them, and they are kind of spinning around and flying apart. So this gave us, after watching these simulations, you can predict, and this has been confirmed by more simulations, that non-self-intersecting loops are planar. I mean, not exactly planar, but almost planar. And they are rectangular with 4 kinks. And you can give analytic arguments to show that they must have 4 kinks. And they have center of mass velocities, which are at the velocities that they're flying apart, of roughly velocity of light by square root of 2. And they have angular momentum, they're spinning around, otherwise they would collapse. It's the centrifugal kind of force that keeps them, prevents them from collapse. So in this way, you would know the shape of cosmic string loops. Okay, so now let's come to gravitational radiation. You have this energy momentum distribution on a loop, and it's highly time dependent. And you want to know how much does it emit in gravitational waves. So a simple estimate is to use the quadrupole approximation, like we did 2 days ago for the domain walls. So the quadrupole approximation is that the dE by dt, that's the power emitted, is Newton's constant, and then the third derivative of the quadrupole moment squared. So g is, of course, g. The quadrupole moment is the energy density times 2 powers of length. So sorry, the mass times 2 powers of length, so that's ml squared, and then you square it. And then the triple dot tells you how fast this thing is spinning around. And so that is each dot gives you a factor of omega, so that's omega to the 6. But for a string, the time period of rotation is 1 over L. And remember that m, the mass of the loop, is going to be the mass per unit length times the length. So you have L squared from m squared. So that's L to the 6, and then there's omega to the 6, and the 2 cancel. So you're left with a simple estimate that the power emitted by a loop is independent of the length of the loop. It's just g mu squared. Okay. So that's a rough heuristic derivation of how much power in gravitational waves is being emitted. And you can actually take loop trajectories and calculate how much power they radiate. And there's a coefficient of about 50 that comes in front. And there's only some weak numerical dependence on the shape of the loop. So this is kind of a universal result. But then you ask, well, what's the spectrum of the gravitational waves being emitted? And here there's a bit of a problem because the quadrupole approximation breaks down at the cusps. And so then you have to work with the energy momentum tensor. So this is the energy momentum tensor of a string. And then you have to solve the gravitational wave equation, and you have to calculate the energy emitted in each harmonic. There are ways you can kind of get these results analytically, but what you find is that the power emitted in the nth harmonic basically is n is like the frequency. It's going as a frequency to the -4/3 for emission from a cusp, a -5/3 emission from a kink. And when these corners collide, these kinks collide, then you get emission that goes as 1 over frequency squared. But when you sum up all these powers due to cusp, kink, it's kind of consistent. So the total power is still 50 g mu squared. All right, so that's the spectrum. There's another issue, like I showed you over here, like at a cusp. So of course the cusp is very relativistic. So there's lots of gravitational waves coming off as well. In these simulations, gravity is not included. So there's gravitational waves that will come off, but there's also this field theory radiation, the radiation of massive particles. So the cosmic string is not only losing energy by gravitational wave emission, but also by particle emission. And the question is, how do the two compare? Okay, because if it's mostly particle emission, then the gravitational emission will be suppressed, and if it's mostly gravitational radiation, then you can forget about the particle radiation. So that question needs to be settled. So earlier the particle emission was kind of ignored because it was thought that the loops are very large, they're cosmological. How can they be emitting particle radiation? So, but when people did the same simulations using field theory, then what they found was a lot of particle emission. And there's a claim that strings, cosmic strings, would mainly decay by particle radiation. And this is sort of a crucial question to resolve because the predictions for LIGO and other gravitational wave observatories depend on how much of the energy goes into gravitational radiation. So what I did with my collaborators is to solve the field theory equation. So remember, while the conclusion over here was that you took a box on the computer, and you throw down these phases and you do the full network simulation. And you find out how many particles are being radiated. But that lacks resolution, okay? Because now you have, maybe your box is, what, 10,000 cube or something, even in the largest simulations are like 10,000 cube. Even then, I mean, you have to resolve the width of the string in your field theory simulation. So it becomes a little difficult to get good resolution. So what we did was to actually solve for one loop in this 10,000 cube kind of box. And there's some technical note about how to solve it, applying numerical relativity techniques to field theory simulations. Maybe I should discuss this separately if any of you are interested, and I can also share the computer code if you're interested. Nonetheless, this is kind of a new technique to solve these field theory equations. Now, the other question is, how do you set up the loop? You have to set up initial conditions so that you can then evolve it using the equations. What we did was we took 4 strings, so 4 straight strings. So we know the solution for straight strings, 4 strings. And then we boosted them, and we can do the boost kind of analytically, right? It's easy to do a Lorentz boost on a field configuration, but not easy is not the word. But yeah, you can do it. The problem is that these codes are written in temporal gauge, where the 0th component of the gauge field is 0. But once you boost, then you induce the 0th component, so then you have to do a gauge transformation, bring it back to temporal gauge. Anyhow, those are technical details. And then you always use periodic boundary conditions because they are the easiest to implement, and that requires some more technical issues. Anyway, so there are 4 strings, and this one is moving to the left, this one is moving to the right, this one is moving to the left, I guess. This one is going somewhere. So when this happens, the strings cross at these points, and when they cross, they reconnect. And so you get a loop over here, and the loop has some angular momentum because V2 and V1, there are some arbitrary velocities, so the loop starts spinning. So you will see that. Here's the setup. So there are 4 strings, and we let go. And we keep track of the particle emission. So you see wherever you see this fuzz coming off is where particles are being emitted. And you see whenever there are corners which sort of cross, you will see a larger amount of particle radiation. Again, it's mesmerizing, I think. So you see some fluff went off, and that was the particles being emitted. And as it shrinks, it oscillates faster. And then eventually it annihilates, it goes away. So the question is, how do we calculate the particle emission from this? And then how does it compare to the gravitational wave emission? So, so we see that if we plot the energy in the string versus time, the energy is kind of flat, and then all of a sudden it crashes, and goes flat, crashes, it goes down in steps. And basically these steps, the time of the steps are correlated with the time at which these corners actually collide. And so there's a definite particle production at kink collisions. And we did this for several different loop sizes, and we found the same features. As a result of this, we can plot the lifetime of the loop as a function of how how long it is or how much energy it has, and we get a straight line, which means that the lifetime goes linearly as the length of the loop. And this is to particle emission. So the lifetime to particle emission, sorry, no, this should be squared. I think these are log-log plots, yeah? The log-log plots. So this is actually particle, the lifetime to particle emission goes as length squared. On the other hand, the lifetime to gravitational radiation goes as proportional to length. And this you can see because, remember, the power radiated, so that was dE by dt, was something like g mu squared, right? Maybe with a 50 or something. And so this is independent, so you just integrate this and you find that the energy lost goes as the time. So it's linear in time. So, so tau, the lifetime in gravitational emission goes as the length. And so you have a crossover. Basically, small loops are primarily emitting particle radiation, and large loops are primarily emitting gravitational radiation. So you have a criterion that the lifetime in gravitational emission is less than the lifetime in particle emission for large loops, so meaning that large loops are primarily emitting in gravitational radiation. And there's a critical length which is the width of the string divided by g mu. And if you put in numbers, then you find that strings with tension above the QCD scale primarily decay by gravitational radiation in cosmology. So, but if you remember, we start with a large loop, right? It emits gravitational radiation, becomes smaller, and then once it becomes small, it starts emitting mostly particle radiation. So there's a switchover, and in fact, this suppresses the gravitational radiation from small loops. Okay, so there's a high frequency cutoff on the gravitational wave spectrum due to particle radiation. Okay. All right. So now that you know how much one loop emits in gravitational radiation and particle radiation, you can sum up over all the loops in this network, and you can include cosmological factors like the expansion of the universe or change in degrees of freedom, radiation to matter transition, and so on. And in the end, what you find is that at omega and g in gravitational waves, this is the energy density in gravitational waves divided by the critical density is something like this. Omega of gamma is the energy, the omega in photons. But the remarkable thing about this is that there's no frequency on the right-hand side. So the spectrum, this spectrum is actually flat. But there are additional factors. So this calculation, there are some. So this calculation actually ignored loops in the matter-dominated era. It ignored particle radiation, and there's some question about the loop spectrum that I'll come to in a minute. But the final result is that the omega in gravitational waves versus frequency plot looks something like this, that you have very small, at small frequencies, the energy density is low, which rises, and then it becomes flat. These are the loops in the radiation era. So these are the loops in the matter era. These are in radiation era. And then there's a cutoff, and the cutoff is due to the effects of particle radiation. So this is the spectrum, and And then there's, of course, these are the experiments. Actually, I thought I had the NANO-Grav. Oh, right, yeah. So the NANO-Grav observations are somewhere around here. And so you can see that the fit is not really very encouraging at the moment. Yeah. So people have tried different things. There are strings which break up and they go away, or it could be that string theory cosmic strings can provide a better fit because they have a smaller reconnection probability, means that they don't annihilate so quickly. There are more strings, so these curves get lifted up, and there are larger loops because the loops don't fragment as much, and so this sort of this spectrum shifts to the left. So who knows? But the picture will become clearer as time goes on. So there's another effect that wasn't taken into account until recently, which is that when you emit gravitational radiation, it actually pushes back on the string. That's called the gravitational back reaction. And recently that has been taken into account, and we get slightly about 10% different plots. In this plot, this came out just maybe a month ago. The particle radiation is not taken into account. Otherwise, these curves would do something like this. Okay, so yeah. No, I don't think it affects the better. Yeah. Okay, so that was the stochastic background. So where we summed of the gravitational waves over the entire distribution, all the loops in this thing are taken into account, and that just forms a background. But Damur and Vilenkin pointed out that you can also see individual bursts of gravitational waves because there are these strings have cusps on them, and the cusps emit a lot of gravitational waves. So here's supposedly a cusp event that's emitting gravitational waves in a conical fashion, and the amplitude is at Earth is given over here. G mu, of course, and L is the length of the loop, and Z is the redshift of the loop, and R is the distance at that redshift. So how big is this cone? The opening angle of the cone depends on the frequency of the gravitational wave, and it goes as frequency to the -1/3. And using this, they predicted that you might be able to see these individual bursts from strings, and depending on G mu, you might be able to see something in LIGO, LIGO 1, and then LIGO 2 is, you have more possibilities. And then the stochastic background that we talked about is down here. So this is one possible signature for gravitational wave bursts, and they did a more detailed analysis of exactly when this might be observable above the background. But you can also have bursts from kinks, because what kinks do is they emit in a sort of a fan-like region, and this fan keeps, so that as the kink is moving, this fan is kind of sweeping in this fan, and so you would see some burst from a kink as well. And then when kinks collide, then also you have a burst. So Damur and Vilenkin again looked at the kink signature. It's a bit lower, but in principle it is there. But yet another signature is that these gravitational wave bursts would repeat, because your loop is periodic. Remember, we saw the animation, the loop is spinning around, and every time it comes in a certain position, it emits a burst. So the loop dynamics is periodic with period L/2, And so you'll get a burst every L by 2. And so the critical thing here is that the loop, the cusp, is emitting in a certain direction, but when it comes around, it should not change its direction, right? It might change its direction due to back reaction, and so you have to estimate how much does the back reaction change the direction of the beam. And so you can do a simple estimate. I theta dot is the, so I is the moment of inertia, and so the change in the angular momentum is g mu squared L, and I is basically mu times L cube, because it's, yeah, so it's mr squared, so it's m is mu, mu times L, so it's mu L times L squared, so that's mu L cube. And so the change in the angle of beaming turns out to be g mu, and which is of course much less than the width of the beam, which is depending on the frequency. But it turns out that g mu is a very small quantity compared to this for the experiments in question. And so LISA, for example, will be sensitive to repeated bursts if g mu is larger than 10 to the minus 10. So there are two constraints. One is that this be small, that the beam angle not change very much, but also that the amplitude be large enough that it can be observed. Okay, so yeah, so you have to ensure that the gravitational wave burst is observable, so it should be above the threshold of the experiment, and then you have to fold in how many loops there are, how many are pointing in your direction, and so on. And it turns out that LISA will be sensitive, so we have how many repeated bursts would you see if you wait for a certain period in time, and you see that LISA would observe about order 10 bursts in about 1 year. So we have to wait for LISA. So just to summarize the signatures, the gravitational wave signatures of cosmic strings, you have a stochastic background, which these pulsar timing arrays are looking for. Then you have gravitational wave bursts from cusps and kinks and kink-kink collisions, and LIGO LISA would be sensitive to that. And then you might have repeated gravitational wave bursts, which again LISA would be sensitive to. So there are three different ways to go after cosmic strings using these gravitational wave observatories. But I would like to also give some sort of caution that there are uncertainties from the string point of view, which are like how many loops are there. And there are three different groups which are kind of have overlapping results, but there are some differences which are important. So there's a group, Blanco Pelado and Olum, they've been doing Nambu-Goto simulations, and they find that the loops have some distribution, which is sort of scale invariant, consistent with being scale invariant. Then there's another group, Ranjewal, Sakuriadu, and Boucher. I think Maria was supposed to be here. They have Nambu-Goto simulations, and they find an excess of small loops, and they use some analytical results on what the distribution of small loops should look like, based on work by Roca and Polchinski. And then Hindmarsh and collaborator have been doing field theory simulations, and they essentially find no loops in some sense, and I'll show you their animation. This, in my mind, I mean, field theory simulations don't have the resolution, but they've been doing a careful job and going to ever bigger simulations. So you've already seen this one, so I'm not going to play it again. So that was the field theory for one big loop that was constructed in this way, okay, using these straight strings. So what the Hindmarsh and collaborators do is that they have a box and they run the whole network of strings, and then they have loops in that network. So they extract one of the loops, and then they say, I'm going to zoom in on this loop. And they zoom in on this loop, and the loop shape looks something like this. And see the size of the box is 256. It's a relatively small box. But when they evolve it, this loop looks as this. So you see there were no oscillations. There was nothing. It just basically collapsed. And I think the reason, one reason might be that, remember that the loops have to have angular momentum. In the other case, we gave these strings velocities by hand, and then they started spinning around. But in this case, they're extracting the loop from a bigger simulation, and basically it has no angular momentum. And so that is why it is just collapsing. And so the question, and the angular momentum depends on the velocities of these strings that reconnect. And so if the strings are moving slower, then of course they will not impart as much angular momentum. So so there is some question of whether this is relevant to cosmology, in the sense because we kind of know that loops have to be moving at speeds of 1 over the square root of 2. And it's not, so anyway, there are question marks. Let me just emphasize it. There are question marks. So Hindmarsh and collaborators would say that loops decay by particle emission and not gravitational waves. And they find that long strings in their simulations have lower velocities, so only loops with small angular momentum are produced. And in this case, also there are constraints, and the constraints arise from cosmic ray observations. But you see, the particle emission in this case is of some heavy gut kind of particles. And then the question is, if you want to connect that to, say, the observation of, I don't know, whatever cosmic ray observations, then it depends on how you convert those heavy guts particles to the particles we know, like muons or whatever. So there's, but these field theory simulations have been challenged by Blanco Pilaro et al. They confirm Nambu-Goto evolution very accurately, except briefly in regions of high curvature. So for example, here there's a loop, and the loop, the blue, I think, might be field theory, and there's a red in here as well. So it's actually two different curves over here, and one of them is field theory, and one of them is Nambu-Goto. And you see with time, the red and the blue keep overlapping. They keep overlapping. Maybe you can start seeing the red separately over here. And then over here, when there are very regions of high curvature, you find some departures. So they really question the field theory simulation, and their claim is that the Nambu-Goto is giving an accurate result. Okay, so Ranjewal and Saklaradu and Boucher and Ranjewal and Tsuyama, so they basically get the same kind of spectrum at long loops, but at small loops, here the spectrum is falling off, whereas here they get a flat result. And so their gravitational radiation is much stronger because these small loops are giving much more gravitational radiation. So, and they both derive constraints, but their constraints on G mu are all in this ballpark. But the strings that we've been talking about, like the abelian Higgs strings, are not the only strings. you can have strings with junctions. So you can have particle physics models where you have two strings that come, three strings that come into a node. So this is when the first homotopy group is Zn. You can have superconducting strings in which the strings are like wires and they can carry current. And then if you have currents on strings, then they can also give fast radio bursts. So that's a separate field of study. That's another observational tool for superconducting strings. You can have non-abelian strings that haven't been explored as much, which is that the strings, so this blue string was here, when it tried to cross, there was a bridge that formed between the blue and the black string. There are strings with different colors, and then they can't really pass through, and so you form a kind of a mesh. But this has not been explored as much. And then there are global strings, which are currently being explored a lot because of the interest in axions. So maybe let me say a word or two about them. So global strings are basically the same model, the abelian Higgs model, but you turn off the gauge field. So there's no gauge field. But the symmetry is the same. It's a U1 symmetry. This only depends on mod phi. So you can rotate phi by any angle, and you still are in the vacuum manifold. I mean, so this action is invariant under the U1 phase transformation. And so this has global string solutions. And so you want, well, okay, the structure of the string is the following, that you have this core, which I described last time, which has thickness of M inverse. But the difference is that in addition to this core, there's a whole cloud of Goldstone bosons which wraps around this core. So it's like a string with a fluff around it, and the string is trying to move, and the fluff has to move with it. That fluff is the Goldstone boson cloud. So as the string moves, it emits Goldstone bosons. To calculate this Goldstone boson radiation, there's a transformation. You can go from this action to what is known as the Karl-Ramon action. And so the Karl-Ramon action has this Nambu-Goto world sheet. It has the field strength squared for a two-form field, and then the two-form field interacts with the world sheet of the string. And this coefficient is fixed by the topology of the winding. Anyway, there's an alternate description of this model in terms of this. And then using this model, you can actually calculate the Goldstone boson radiation. But so the question is, what does a loop do? And so we did a very similar setup to what I described earlier. We took these four strings. This is actually at a later time, so it's not so clear. And here we're plotting the total energy, and here we're plotting the potential energy. And in the potential energy, you can see very clearly that you form a loop. Let me try. Okay, so we started, and then so here's the loop, and you can see it's much more fluffy. There are many more vibrations on it, and it just basically collapses. So unlike the gauge string loop, which oscillated for a long time and it slowly shrank, this global string loop basically quickly shrinks and disappears. So the evolution of global strings is quite different from that of gauge string. And there's at least there used to be a debate. I don't know if it has been settled. The question is, what is this emission of Goldstone bosons? Because those Goldstone bosons are axions. Okay? So, and if you can find the spectrum of radiated axions, then you can tell whether they're detectable or not detectable, because the detectability depends on how much power there is at a given frequency. So the Karl-Ramon action calculation that we did earlier shows that there's a sharp spectrum which is peaked at a wave number of 1 over L, where L is the size of the loop. and the numerical evolution agrees with this spectrum. Well, maybe I shouldn't go into too many details, but anyway, there have been, in particular, because there have been recent simulations. I don't know, is there a talk on axions over here? No. Anyway. Okay, let me just conclude then. So cosmic strings occur in various high energy theories, and they have rich dynamics and interactions. Cosmic strings decay by gravitational radiation and particle emission. So you have to think about both of them. The stochastic background of gravitational radiation may be sourced by cosmic strings. I think it's a bit early to say, early to exclude them. And if you start observing gravitational wave bursts, then you can directly detect cosmic strings. And I think repeated gravitational wave bursts would be a unique signature of cosmic strings. I don't know of any other source that gives a repeated gravitational wave burst. There are lots of different kinds of strings with junctions, superconducting strings, non-abelian, global, which can all be interesting. And the evolution of global strings is important for axion cosmology. Okay, with that, I'll take questions.
Okay, thank you, Professor Vachaspati, for the nice lecture. Are there questions?
Yeah, so you mentioned that field theory, depending upon which field theory you use, the strings, the cusp can produce particles. So,
sorry, that strings are?
The particle can be produced from the cusps and kinks.
Yes.
So, can it in some way affect the baryon number present at the time when the strings are emitting this?
Yeah, so if the particles on the string carry baryon number, then they could affect. Yeah.
But will they be produced in equal, like net baryon number?
You mean the CP violation?
Yeah.
It depends on the. So I don't know of models in which you can do that. But you would somehow have to feed in the CP violation in their decay. In the decay of those particles to baryons, you would have to put in CP violation.
But standard model already has an inbuilt CP violating sector, so I think.
But very small.
Yeah.
There.
So I had a question about this calculation of gravitational waves from strings. You said that the strings are relativistic objects, they are moving at the speed of light. And you are showing this, this estimate where you are using the quadrupole formula. Now I suppose there are modern calculations which take into account that this approximation doesn't work for relativistic objects, and yes, there are proper calculations for that.
Right. So, I mean, I gave that estimate just to show that the power emitted is independent of the length of the loop. But the other calculations were done in the full formalism, not using the quadrupole approximation. So yes, so we took a whole array of loops, and we put the T mu nu for each of them, and we calculated the H mu nu, and then the power. So we did all that. Yeah. Thank you. Yeah.
Okay. Are there?
So for cosmic strings, so they are actually whatever I have read in Milenkian Szilard book. So if I have a Mexican head potential at phi 1 equal to phi 2 equal to 0, this point is actually related to the string core. So as we have know, as far as I know, that when we apply quantum field theory, so we just do the just introduce the quantum fields about this classical minima. But as these cosmic strings are phi equal to 0, this is not the minima of the potential. So how can we say about this Goldstone emission for global strings? So they are the quantum fields.
Let, let me, sorry, let me pull up that slide first. Let's see. So, well, one way to think about it is that that this is like electromagnetism, except with one more index. Yeah. And then this is a J mu A mu type of coupling. So there's a current which is proportional to the string worldsheet, and then there's this gauge field. So you take some string moving in some way, and so you know what sigma, the current you know, and then you just kind of solve the Maxwell equations, and you would get the radiation. So so you don't have to deal with this phi at all. Yeah. So the Kalb-Ramon, there's a transformation from phi to these variables b mu nu. I think maybe Ashok would know this better, but it's something like sorry, I call it b mu nu lambda. Maybe 1/6 of epsilon mu nu lambda rho d rho phi, something like that. There's some transfer. Is that right? Okay. Okay, but anyway, there's a transformation between the first derivative of phi and this field strength. Sorry? Yes.
Another question is, if in a complicated theory there is local strings and global strings, can they do merge and loop form a loop? So one side is local, another side is global.
No, because the topology has to continue. Right? I mean, you can't.
Topological charge should be conserved.
Yes, the topological charge should be conserved. Yeah.
Thank you.
You were writing, so if there is a matter field, like if there also massless, they will also contribute to this?
So yes, so you can have a situation where there are fields that prefer to live on the string. And then as the string moves, you will start emitting those particles as well, and they will appear as cosmic rays. So that has been considered as well, yeah, where there are excitations on the string.
Are there other questions?
You talked about the high frequency cutoff. So there is another cutoff coming from the Frickson domination at early time. From the Frickson domination, like cosmic strings like scattered with other particles in the plasma.
Oh, from the friction, I see.
So what about the comparison?
So that friction happens at least for gut strings, it cuts off very early.
Yes.
So that's on a very, very, very high frequency.
Yeah. So the particle production in your case is that cutoff is much lower.
Yes.
Are there other?
This radiation of scalars, I think it will require a change in the dipole moment of the string. The rate of change of dipole moment will give you so when you calculate from this.
No, the equation would look something like box B mu nu force is going to be
But this B mu nu is, it's equivalent to a scalar or not in the end?
to a vector. So
Okay.
this is like
So even vector would require a change in dipole moment then, right?
so it's the source. The source is something like d sigma mu nu, some delta functions. So the string, the moving string, so it's like a moving wire. So if you shake a wire, then there should be some radiation. So there's no real dipole moment, as far as I know. Oh, I see what you mean. It's like the quadrupole moment. Yeah, that maybe. Yes, yes. Maybe you can think in those terms. I haven't thought of it in those terms.
Okay. Are there other questions by anybody else?
I have a naive question. So the simulations, how computationally expensive they are?
The Nambu-Goto ones are not that expensive. I mean, they depend on how big you make them. But the field theory simulations are very expensive. So, but now somehow people are going to, I think the largest I might have seen would be 24,000 cube. But then they are also using adaptive mesh refinement, which effectively boosts it to something like 240,000 cube. So with adaptive mesh refinement. And those, like some of Mark Heinmarsch's simulation, people say that they consume 1/4 of Finland's computer resources. I'm not sure that's true, but I wouldn't know. But yeah, they are very sophisticated. All these simulations are getting very sophisticated. And then now they start calculating gravitational waves and yeah.
Okay. So this is a bit contrived, but Pierre and Chiara, they wrote a paper with the EPTA, where one of the models, I think this is the LRS, so Maria's model, they constrain the string tension to 10 to the power minus 10.6, roughly. I mean, there are many uncertainties in these things. So I'm not sure if it really works, but if this was, let's say, the correct value of the string tension, what would that do for strings in the Lisa band? So I guess what I'm asking is, how precise was that inequality that you had? Does it really have to be greater than 10 to the power minus 10, or can it be close to 10 to the power minus 11 as well?
For the repeated bursts, you mean? I'm trying to get to that. Yeah, you mean over here? Yeah, I mean, if G mu is less than 10 to the minus, like if 10 to the minus 11, then at least our estimates don't. But there is a catch, I think, over here, which is a good point, is that these estimates were made with Ohlum and Blanco-Pelado loop distribution. If you use the other Rangeval et al. Loop distribution, the predictions might be different. And I think it would make it more optimistic because there are many more small loops. So These bursts, yeah. Yeah.
They should be very recent. So the EPTR NANO-Grav, they like give constant on the stochastic background, and these are burst. They are very recent burst, right?
They are relatively close by,
Yes,
yes.
and so there is no relation with that stochastic constant, because if the string like experience some inflation, they can re-enter the late horizon, then the gravitational wave will be very suppressed, right? Then in that case, you can look for the burst, but not for the gravitational wave.
For the stochastic background. Yes, you could imagine that situation.
Yes.
Where you would see these, but not the other, yeah.
I think Dhruv has a question.
Hello. So I just had a very basic question about how the simulations work actually. Like you showed that 2D grid, right? So that is okay if you want to see how infinite means 1D strings look like. So to get the number of loops, and then you said that they are scale invariant. To see that, you need to do a 3D simulation.
Yes, yes. So we did that in 3D. At every lattice point on a 3D lattice, we throw the phase, and then through each plaquette, we calculate the winding, and then we connect the strings and we see what shape they take. So those simulations are in 3D.
And also, what is the relation between, say, the size of the grid versus, the individual grid size and the length of the grid?
Yeah, that's a very good question. So remember I said symmetry is the only important thing. It's not completely true, because as you said, the size of the lattice, you're assuming that the phase at one point on the lattice is independent of the phase on the other side. So you really have to find some correlation function and then say, well, there's no correlation between this point and this point, so I can treat them as independent. So the lattice spacing is the correlation length. And there's a whole, the actual value of the correlation length depends on the details of the phase transition, whether it's first order, second order. And so there's, I don't know if you know about the Kibble-Zurek type of arguments. They try and make some arguments as to what this correlation length is.
Because this theta can vary, it's a continuous variable, right? Unlike the domain walls case, where you could have discrete values.
Yes.
So it is possible to have very close thetas. I mean, you don't need to have independent theta. I mean, it can vary continuously. You can have arbitrarily close thetas. So then how do you, but still you're saying that the correlation length plays a role here.
So
also.
after this, I mean, the dynamics of the symmetry breaking would imply some correlation length.
Yes.
For example, if you have first order transitions and you have bubbles nucleating and colliding, maybe the size of the bubbles at percolation gives you the length.
Yeah.
So then you say that the lattice spacing is given by that. But it doesn't affect the spectrum of the loops. It doesn't affect the existence of these 80% in infinite strings. It only affects the sort of the overall scale of the simulation.
And I was also wondering about, I mean, how do we model the emission of particle radiation when taking numerical simulations?
So in these it's just classical emission. So you calculate the energy. Actually, we calculate the energy in the string. So we say the string has phi equal to 0 at the center. So we arbitrarily say how much energy is there up to phi of 0.25 or something. And so then we just calculate the energy within the core of the string, and we say that the rest of it is gone into particles.
Okay. If there are no more questions, let's thank Professor Vachaspati again for the excellent talk. And we will meet at 11:30.